Hello and welcome to this tutorial on ultrasonic intensity. Ultrasonic intensity is defined as the flow of ultrasonic energy per unit area, but there is still sufficient ambiguity in this definition to mean that there could be multiple possible intensities of interest, as we shall see throughout this tutorial. It's also important to realise that this is a derived quantity and not a directly measured quantity like pressure or power. Ultrasonic intensity is widely used throughout the standardisation process. If we consider just the IEC family of documents, we note that there are multiple documents in the diagnostic, physiotherapeutic, and HIFU, HITU and lithotripsy considerations, all of which use ultrasonic intensity as a means of field classification and characterisation. Starting with a theoretical basis for ultrasonic intensity derived from power, we go back to our original definition, which was that intensity is the flow of energy per unit area. Well, work done per unit time is simply power, and therefore intensity is power over area. We can measure power directly with a radiation force balance. And for those people unfamiliar with radiation force balances, there is some useful background information on another tutorial video in this series labelled Ultrasonic Power Measurement, which can be found at both the Precision Acoustics website and on our YouTube channel. We could also consider a theoretical basis for intensity starting with ultrasonic pressure. Here, intensity is the time-averaged product of pressure and particle velocity. Pressure we can measure directly, but at ultrasonic wavelengths particle velocity is very much more challenging to measure directly, and in practice normally not possible. If we're able to consider a plane wave approximation, then the relationship between particle velocity in pressure is simply to divide by the acoustic impedance of the medium, which is its ambient density and wave speed product. Note that if waves are not plane, this relationship does not hold, and therefore the next relationship, which relates intensity to pressure squared, is not valid. However, we are assuming we've got plane wave approximation, and so we can simply say that the time averaged pressure squared divided by acoustic impedance is a good measure of intensity, and often the RMS pressure is an adequate representation of time-averaged pressure. Let's start to consider what happens when we look at different amounts of spatial variation. So if we consider an ultrasonic transducer that's radiating with a beam pattern here, and I've shown a beam pattern that's pretty common for circular plain piston transducers. If we determine a measurement plane in the far field of this transducer, we could simply look for the peak value of pressure anywhere within that measurement plane. However, we could also consider averages of pressure over different areas, and all of these values will lead to different intensities because the area is changing. Now let's look at temporal variation. Here we have a typical diagnostic ultrasound waveform. We notice that one of the definitions of intensity involved a time average of pressure. And if we just look at the peak value of pressure, this will give us a very different value to that which is averaged over the pulse duration, or that which is averaged over all time. And here I'm showing an example where the pulse repetition rate is 40 microseconds. So depending over what level we are averaging our pressure, be that an instantaneous one for a peak, a pulse average, or a time average, we can get the same level of variation as we did when we considered our spatial variations with spatial peak and spatial averages. There's another correction which we need to consider as well. Most of the measurements which we make for ultrasonic pressure are conducted within a water bath with a transducer and a hydrophone. However, most of the applications of ultrasonic intensity are attempted to try and represent what's going on within the body. If we look here at the absorption values that we see for various common media, many of which are biological, but also we compare that to the water absorption level, which is at the very bottom of the graph, we can see that there are substantial differences in the overall level of absorption. Therefore, if we are making measurements in tissue, we're likely to see very much smaller pressures and therefore very much smaller intensities because signal has been absorbed getting to the path. In fact, this absorption is going to be dependent on both frequency and distance travelled. So it's got a dB per centimetre per megahertz variation. Given the large range of different values which we see for different biological tissues, it's been decided to standardise upon a level of 0.3 dB per centimetre per megahertz when attenuating pressure and intensity values for measurements that were made in water but are then to represent those that will be made in biological tissue. So when we're talking about intensity, we really need to ask which one. We've seen that there can be spatial peak or spatial averaging intensities. They could have temporal peak, temporal average, or pulse average temporal variations. And we may look at those with and without tissue correction, so they could be linear or attenuated. And we can have any combinations of all three of these spatial, temporal, and tissue correction factors. When we're looking at therapeutic transducers, it's very common to consider the output beam intensity. So rather than working from a pressure basis, this goes back to working from the power basis. Here we're looking at the time averaged power divided by the output beam area of the transducer. Now this output beam area is often determined with hydrophone, very close to the transducer, and you're effectively measuring the area of the radiating aperture of the transducer. We also need to consider focal intensity. So if we consider a transducer and a measurement plane in front of it, then we can define the output beam intensity, as we saw on the previous slide, as the time averaged power radiating through that output beam area. However, for a focused transducer, all of that power is then going to be concentrated in the focal plane through a very much smaller area. And so the focal intensity, whilst it still uses the same time averaged power as we previously had, is now divided by the very much smaller focal area. Because the area of the focal plane is very much smaller than the area of the output beam plane, we find that the intensity of focus is very much larger than that of the output beam intensity. Having decided that we're going to measure the beam area with a hydrophone, there is still some ambiguity over exactly how we determine that beam area that we need to resolve. Consider here a circular transducer radiating at a continuous 1.5 MHz, 2.5 centimetre diameter, and measured at an axial distance of 20 centimetres from the transducer, so well in the far field. We can see that if we look at the -6 dB level down from the peak, we can determine one particular beam diameter. But at the -12 and the -20 dB levels, this gives entirely different diameters and therefore areas. In fact, if we look at those -6, -12 and -20 dB limits, we notice that there's nearly an order of magnitude between the areas that we derive by determining the beam areas at each of these different cutoff thresholds. You may ask, so how much does all of this matter? So let's consider a few examples. If we consider a typical HIFU transducer, we can see that we have an output beam intensity that's been derived from 130 watts of power radiating through an aperture of 6 centimeters diameter, which is 3 centimeters radius, and therefore we see an output beam intensity of 4.6 watts per centimeter squared. At focus though, the focal spot is typically 3 millimeters across, so 0.15 centimeters, and therefore we get a focal intensity of nearly 2 kilowatts per centimetre squared. Considering now the Food and Drug Administration's Track 1 limits for peripheral vessels, and here we're thinking primarily in the context of diagnostic ultrasound, we can see that the ISPTA limit is 720 milliwatts per centimetre squared. Noting carefully, ISPTA 0.3 refers to the fact it is the spatial peak, temporal average, derated at 0.3 dB per centimetre per megahertz. The ISPPA 0.3 limit, so spatial peak pulse average, derated at 0.3 dB per centimetre per megahertz, is 190 watts per centimetre squared. In each of these two cases, there are nearly 3 orders of magnitudes variation between one of the factors, IOB and iFocus for the HIFU case, or ISPTA 0.3 or ISPPA 0.3 for the diagnostic case. All we've done is change the averaging, be that the average area in the therapeutic case or the time averaging in the diagnostic case. So to summarise then, there are many ultrasonic intensities, and it's important to specify which one is both of interest to you and which you are reporting. Moreover, the definitions of the different intensities vary wildly, so it's important to carefully check the relevant standard that you are working to. We hope you found this tutorial interesting. If you did, please come back and find some more of the videos in the Precision Acoustics tutorial series.